Welcome back to our series of hydrolysis of carboxylic acid derivatives. Okay, now you may notice I have a different associate with me this week. If you recall from the previous video, Professor Penelope Pigtails had a bit of a fall. We consulted with one of the physicians on our set here. Turns out it was a mild concussion, so doctor recommended some bed rest, so she's taking a little break from it. But I'm sure Donkey here can do a fine job of supervising me, make sure I don't screw up my elementary mechanistic steps, put them in the wrong order, or silly things like that. So, all right, well, let's look at how we can hydrolyze an amide. Now, amides are like a rock. They're the rock of carboxylic acid derivatives. They're very stable. So it's hard to hydrolyze them. So we're going to need some really, really forcing conditions. So we're talking like if it's basic conditions, 40% sodium hydroxide. If it's acidic conditions, we're talking like 6 molar HCl. Okay, so you really got to beat on an amide to get it to hydrolyze. So that's what we're going to do. Okay, we're going to throw in a strong base. Okay, and the amide we're going to hydrolyze here is this amide. If you recall, an amide is a carbonyl that has an alkyl group on one side and a nitrogen on the other. Okay, and we're going to react this with sodium hydroxide and water. When we say 40% sodium hydroxide, we're saying that 40% of this is the sodium hydroxide and the other 60% is water, unless it's specified that the solvent is something else. And that 40% is probably weight per volume. The sodium hydroxide is a solid, and a solution of sodium hydroxide in water is a liquid. But let's not talk about general chemistry too much here. This is organic chemistry. Okay. So there we go. So we're gonna, that is not the product we're gonna get. All right. The product we're gonna get is this carboxylate, sodium acetate, plus methylamide. There we go, that's better. Okay. So hydrolysis, we're using water to hydrolyze, or in this case hydroxide, because it's basic conditions, to hydrolyze that amide bond. Okay, let's look at a mechanism of this reaction. All right. Always start our mechanism with a reactant. Okay, in this case an amide. Alright, and this is going to be very similar to the mechanism that we used for hydrolysis of esters under basic conditions. Okay, first step, I've got a strong nucleophile, so we're gonna start with this, which is a nucleophilic addition. Okay, and you're going to note that this intermediate here has a negative charge. Okay, a net negative charge in this intermediate. Okay, and that's what we're going to be looking for in a base. A nucleophilic acyl substitution under basic conditions. If you find yourself drawing an intermediate that has a net overall positive charge, then you're heading down the wrong path. Okay, you're probably trying to draw an acid catalyzed reaction. Okay, but anyways, nucleophilic addition. All right, and then this is going to leave. Okay, that's a nucleophile elimination. Ooh, that's EL. Okay. And that gets us to, where do I want to put this? A carboxylic acid after that, plus the conjugate base of methylamine. Okay, this has got a negative charge on it. This is fairly basic. This is a weak acid, so we're gonna end this up with a proton transfer. All right, and ultimately gives us the acetate. Okay, we had a spectator ion here, a sodium ion. I didn't even bother to draw it, but it's around. Okay, faithfully watching from the sidelines. Okay. Ultimately, in our hydrolysis, we make the acetate and the primary amine in this case. Now, if this had been two alkyl groups on that nitrogen, we would have made a secondary amine. Okay, and if we had two hydrogens here, we would have made ammonia. All right, so that is hydrolysis of an amide under basic conditions. Thanks for watching.